So, welcome to the next lecture of Math 120. In the previous lecture, we were discussing about the properties of determinants. If you have any question regarding this topic, you can ask. Properties of determinants. Okay. We discussed several properties. One property which I forgot to tell you about, which came into my mind later on, is this property, the determinant of product of two or more matrices is equal to determinant of their respective products. Determinant of A into B is equal to determinant of A into determinant of A into B is equal to determinant of A into determinant of B. We can generalize this property as well. So we can write determinant of A1, A2, so on, AN, any number of the product of any number of matrices. If you want to calculate the determinant of this product, this is equal to the product of their individual determinants. So this is how it works in the determinants. Okay, so this one. But remember that a very important note, which students usually do this mistake, often do, that determinant of A plus B is not equal to determinant of A plus determinant of B. Okay, this is not true, because student, they imply from this property that if it is true for the product of two matrices, then it would be true for the sum of two matrices. But this property is not true in general. Okay, for maybe some particular kind of matrices, it may be true, but in general, determinant of sum of two matrices is not equal to the sum of their individual determinants. So remember this. Similarly, we have many other properties of properties related to the inverse of matrices, properties of other properties, you can say properties of inverses, properties of transpose of a matrix, properties related to the symmetric matrices. Sir, there is a question in the chat, and will quiz be at the end of the class? Yes, Talha. Many other properties you can see in my lecture slides as well as in notes. You can see the book as well. For example, the properties of inverse of a matrix. G beta, is there any
could you
question?
please bring the front board down for a second?
The upper one? Okay.
Yes, sir.
This one. Now, do you have any question?
No, sir. It's all right.
Or you just have to note down these properties. Okay. Now, the properties related to the inverse is that if a matrix A is invertible, then its inverse, whole inverse, is again the same matrix. Means if you take inverse, double inverse of a matrix, then you would get the same matrix. So there is a problem with the picture. No, it's okay. So this is a very good property. You can see, you can generalize this property as well. You can say that if you have, no, let me write another property, then we'll discuss this one as a special case of that property. Another property of inverses is that A into B into C whole inverse, बल्कि पहले दो के साथ लिखें. If A and B are invertible, then the inverse of their product is equal to B inverse into A inverse. The order of the matrices in the inverse here is basically will be changed. Again, if we have three matrices A into B into C, and you want to take it the inverse of these, the product of these three matrices, then it would be C inverse into B inverse into A inverse. So it's basically a cyclic rotation of the matrices. When you take the inverse of a product, then there will be a rotation of these matrices. C would come first, the last one. The second would definitely come on the second, and the third will be come on the, sorry, here. The first will come on here in the third place. So we can generalize this even A1 into A2, so on, AN. If we have a product of n matrices, then the whole inverse is equal to AN inverse, AN minus 1 inverse, so on, A2 inverse into A1 inverse. So this is how it goes. So basically, you can say that a cyclic kind of rotation of matrices in this kind of property. I hope you get it. If you have any question, you can ask me. Some other properties may be related to inverse of a matrix is that if we have a constant k times the matrix A, this k is a scalar. Whole inverse is equal to that constant inverse into A inverse. That constant inverse is what? It is simply 1 over k times A inverse, because the inverse of a constant is what? Multiplicative inverse. What is the multiplicative inverse of 2? It is 1 over 2. So here we have k inverse means 1 over k. So remember this kind of properties related to A inverse as well. I would advise TA to give you tutorials about these properties, give some particular examples of the matrices which satisfy these kind of matrices. So try to attend the tutorials as well so that you can see the examples of this thing. So there's a question in the chat window. Kiran Khakan, sir, can I ask a question? Yes, of course.
Sir,
Kiran, go ahead.
वो एक्चुअली ना थोड़ा क्वेश्चन रिलेटेड है, लाइक पिछले लेक्चर से मैंने ये पूछना था कि मैंने क्वेश्चन देखा था ऐसा कि एक उन्होंने डिटर्मिनेंट दिया हुआ है उसमें लाइक वो के टर्म एक है एंड देयर लाइक कि ये वाला मैट्रिक्स इन्वर्टिबल कब होता है, तो सर वो तो के की मतलब अगर के की सॉरी अगर हम उस डिटर्मिनेंट को 0 के इक्वल करके के की एक वैल्यू निकालें तो उस वैल्यू के अलावा वो सब पे इन्वर्टिबल ही होगा ना?
Definitely.
तो
for what value of for what the question was basically, which I assume that for what value of k the following matrix is invertible or non-invertible? ये question
invertible का पूछ रहे थे. तो
invertible कब है? So you have to put the determinant of that matrix is equal to not equal to 0. Okay.
अच्छा.
ठीक है.
Okay.
तो जिन values के लिए वो determinant 0 नहीं होगा, on that values the given matrix will be invertible, of course. ठीक है.
Okay.
Or in the other way around, you can put that matrix equal to 0 and find the value of k. For those values, the matrix will be singular. Okay? Other than those values, the matrix will be non-singular. It's a vice versa, I think. It's opposite of each other. I hope you get it. Now here, what are these A, B, A1, A2, so on, A, and these are matrices. These are square matrices of any order, okay? Where you can say that these A1, A2, so on, AN, they are square matrices of order, square matrices of same order plus their order could be anything. The matrices should be multiplicable with each other. Similarly, A, B, C are square matrices of order, you can say n order. This was another question in the chat window, that what is A1, A2, so on, AN. I hope you get it. If you have any further question, Muhammad Ahmed Ehtisham, you got it?
Yes, sir. सर मुझे ये नहीं समझ, मतलब ABC वाला पार्ट तो मुझे समझ आ गया है कि किस तरह से इसको मतलब ब्रैकेट ओपन करना है, बट ये A1 A2 सेपरेट मैट्रिसेस हैं क्या है, मुझे समझ नहीं आया.
Yes, A1 A2 so on AN, they are matrices, because you have to generalize this. How can you generalize the product of n matrices?
Okay, sir. Okay.
Okay, I have to generalize the notation as well.
ओके सर, थैंक
सर तो ये
Okay.
सारी जो मैट्रिसेस आप यूज कर रहे हैं इन्वर्टेबल है, मतलब A B?
Yes, of course, they must be invertible. Their determinant should not be 0.
So
Otherwise,
the
how can you write this C inverse
मेरा
if it is not inverted?
सर मैं पूछता हूँ ये जो आपने सारा किया है फॉर स्क्वायर मैट्रिसेस के लिए ना सर?
For square plus invertible matrices, the matrices should be invertible.
Okay, thank you, sir.
All these matrices which we use here in these properties, all these matrices should be invertible. Okay, invertible होंगे तो definitely square होंगे, because it's a basic criteria to start to check whether the given matrix is invertible or not. The matrix should be square. Okay.
So can you confirm this, that have we written this beforehand? Because I think we have done these three formulas beforehand.
These three formulas? These
yes,
one?
sir. Yes, sir.
I don't remember.
नहीं हमने नहीं किया सर.
Maybe I don't remember that I have.
Sure, आपने सेक्शन 3 में थोड़ा सा वो करा दिया था आगे, लेकिन सेक्शन 1 में नहीं.
चलें कोई बात नहीं, अब रिपीट भी हो गया तो नो प्रॉब्लम, रिवाइज हो जाएगा. So some other properties related to the transpose, for example, the transpose of any matrix. If its double transpose is again the same matrix. Now here, the condition of a square matrix is not A may be a rectangular matrix as well. Okay, A need not to be a square matrix in transpose of a matrix. A is any matrix. You can see A is any matrix. Okay, it could be a square matrix. It could be invertible. It could be symmetric, but anything. Okay, it could be a row or a column vector. So there is no condition on a matrix. What kind of a matrix it should be. So A should be any matrix. Then its double transpose is equal to the original matrix. Because when you interchange rows and columns 2 times, definitely you'll get the original matrix. So there are some other properties related to the determinant, transpose. In transpose, A plus B whole transpose is equal to A transpose plus B transpose. Okay. So this property is valid, is true in case of transpose. Okay. Another property related to the transpose is A into B whole transpose is equal to, again, the order of the matrices will be changed. B transpose, A transpose. Okay. We can generalize this property even for the n matrices A1 into A2 into so on. An whole transpose is equal to An transpose, An minus 1 transpose, so on, A2 transpose, A1 transpose. Of course, these matrices, now there is no condition on the order or any other thing of the matrices. So these matrices should be multiplicable. Okay, their multiplication should be possible. Multiplicable. Okay. Similarly, this product is also should be multiplicable. Otherwise, we cannot write left hand side is equal to right hand side. So remember these small things while using these properties. Okay. Another property which is very important, if this is true for plus, it must be true for negative, difference of two determinants as well. Another property related to the transpose is that K times A whole transpose. Now K is some scalar, okay? And A is a matrix. Then its transpose is K times A transpose. K doesn't change anything here in the transpose. K remains the same. Okay?
Right.
Similarly, you can see some of the properties related to the symmetric matrices as well. What was a symmetric matrix? If the transpose of a matrix is equal to itself, then we call it a symmetric matrix. Okay. You can see the properties of symmetric matrices in the book as well as in, I think in lecture slides. I might have given these properties. You look at these properties, otherwise you can see these kind of properties in the book as well, okay? Now, matrices, their inverses, their determinants, linear systems, how to solve linear systems, homogeneous linear systems, and solving them using different methods. This topic has been finished now. Now we are going to start the new topic, which is the vectors in higher dimensions. If you have any question related to this thing, you can ask me. I would advise TAs to discuss these properties with the help of examples in the tutorials. I hope you would attend those tutorials and try to understand these properties more deeply. So let me now start a new topic, which is vectors in higher dimension. Or you can say vectors in Rn. Rn. Now, n could be anything. Rn is usually called Euclidean space. Euclidean space. Okay. As what is R? R is a real line. You know, I hope you know it. What is R? R is a real line. And what is R2? In fact, it is R times R. It is a Cartesian product of real line with the real line. And what does this show us graphically? It is basically a two-dimensional plane where X represents the elements of the first real line, and Y represents the elements of the second real line. It's basically Cartesian product of two real lines. Now, what is a Cartesian product? A Cartesian product is basically a product of numbers in R such that X into Y, we write them in ordered pairs such that X, Y belongs to R. So this is how we define Cartesian product of two sets of real numbers, R into R. Now, if you define R cube, what would be R cube? R cube is nothing but it's a Cartesian product of three real lines. Okay, so this set should contain the elements of this kind X, Y, Z, such that X, Y, Z, they all belongs to the real line. So this is your R cube, which you say usually a three-dimensional space, three-dimensional space. Similarly, you call it a two-dimension space. Okay, two-dimensional space, or you say it a Cartesian plane. Okay, Cartesian plane. You have to remember these terms because it's the basic terminology in mathematics.
So what
you have
is
to
R?
remember. R is a set of real numbers.
Okay.
Huh? You know it? What is a set of real numbers?
Yes, sir, we do know.
Okay, that's great. I hope. R is, I have told you that R is a real line. R can also be specified or denoted as R is -infinity to +infinity open interval. Okay, it's a real line. It's basically open interval which contains all the real numbers less than -infinity, greater than -infinity and less than +infinity, all the real numbers. So their Cartesian product, their graphical representation is R cross R is a Cartesian plane, XY plane. Okay, we also call it XY plane. I hope you know it. In R cross R, you have a three-dimensional space, and you also say it's 3D. Okay. And the graphical representation of R cube is nothing but X, Y, and Z. Okay, This is basically the graphical interpretation of X, Y, Z. Now, usually you might have discussed or studied before that any number or any point in the XY plane is denoted by X, comma, Y, ordered pair. And any number here in R cube is denoted by X, Y, Z, okay? Any point in X, Y, Z. But now we are going to define them in vectors. So vectors are usually denoted as a column vectors, okay? Column matrix, you can say. Now you should define this vector in this way, X, Y. This is a vector now, okay? This is a vector. This is what? This is an ordered pair. This is not a vector, okay? You can write, if this is a vector, X, Y, and you call it some vector, maybe U vector, then the transpose of U is what? Transpose of U is transpose of this matrix, which is X, Y. This is your, the transpose of this vector, X, Y, okay? Now,
can you please come again?
From now on, you are not going to write ordered pairs in this form, X, Y, okay? Because we are discussing vectors in Rn, okay? So you always write vectors in this form, column vector, okay?
Sir, then what is the purpose of taking a transpose by converting that vector form into the original matrix form?
So if you try to write a column vector in a row vector, then it should be a transpose of a column vector. This is how you deal vectors, column vectors and row vectors in vector spaces, okay? Okay, in vectors, there is no, you cannot have a row vector, okay? If you want to write a row vector, then it should be a transpose of any column vector originally. This is how we use vectors in Euclidean space. So similarly here, this is an ordered triplet in usual 3D space. But when we are discussing vectors in Euclidean space or vectors in Rn, then their notation should be X, Y, Z in the form of a vector. And you can call it some vector X, okay? Then if you want to write this thing, then it is basically, it is the transpose of this vector. And it is X, Y, Z, X, comma, Y, comma, Z, this one, okay? Always write vectors in this form. Now, from now on. यार वाकई मैं भी जो है ना दूर रह के तंग पड़ गया हूँ आपसे। अब दिल करता है कि आप जो है ना क्लास में आए।
सर आप दावतनामा भिजवाएं हम आने के लिए अभी हाजिर हैं।
दावत तो वलीमे का भेजा जाता है यार, क्लास का तो नहीं भेजा जाता।
सर इतना आपने तंग कर दिया लम्स ने, तो अब हमारे लिए यही होगा बस।
हॉस्टलाइट्स हैं।
हाँ?
हम जो हॉस्टलाइट्स हैं हम तो आ भी सकते हैं क्लास में। तो
आ जाना, आपको किसने मना किया?
सर वो क्या था, क्लास कहाँ थी? रूम नंबर?
It's in 302. I told you in the previous lecture.
भूल जा रहा है, नेक्स्ट क्लास में आऊंगी।
चलें, that's great. हम भी जो है ना खाली कमरे में पढ़ा के तो क्या कहते हैं, बोर हो गए। इसलिए हम तो ये चाहते हैं कि आप लोग जल्दी जल्दी आएं क्लासरूम्स में।
उस दिन तो हम आए थे लेकिन सवाल सुनने में नहीं आ रहे थे बच्चों के।
अच्छा, चलें, as you think better or as you like better. So now, if you define a vector in R4, now what would be R4? R4 will be R cross R cross R cross R. It's a kind of product of 4 real lines. So you cannot plot it, okay? But you can imagine it. As you see that R cube is what? It's a mutually orthogonal 3 lines, okay? Mutually orthogonal 3 lines, mutually perpendicular 3 lines, which makes R cube. But R4, in order to plot the R4, you must have 4 mutually orthogonal lines. So that is difficult to plot for me even. But you can imagine it. Similarly, R5, and so on, R10, and so on, are any number, R power any number. So these kind of all spaces are called Euclidean spaces. Okay. Even a single R is also a Euclidean space with R power 1, with R power 2, R power 3, R power 4, and so on. All these spaces are called Euclidean spaces. Okay. Euclidean.
What does this term mean?
Euclidean was the name of a mathematician who properly defined these spaces. That's why we call them Euclidean spaces. Okay. You got it? Any confusion? Now, what would be the R4? R4, technically, you should write it in this form. X1, X2, X3, X4 in a vector form such that X1, X2, X3, X4, they all belongs to R. Okay, this is the set R4, which contains all the vectors having 4 components, you can see. Okay, having 4 elements. So if we define R5, what kind of set or a space it would be? It would be of this kind, X1, X2, so on until X5. And all these elements of this vector, they belongs to X1, X2, X3, X4, X5, they belongs to R. So this set is, you can imagine it that it's a basically 5D set. It has, if you try to visualize it, you can imagine that there must be 5 mutually orthogonal or mutually perpendicular lines, which makes this set graphically. Just as R cube 3D is what? Its graphical interpretation is what? It's a mutually orthogonal, mutually perpendicular 3 lines, which makes 3D space. Okay. You cannot plot all of these Euclidean spaces, but you can imagine them. Okay, just imagine them. You don't need to plot them. We are going to use all these kind of spaces while discussing the solutions of a linear systems and vector spaces and many other things you would see in the subsequent lectures. Now, what would be Rn? Rn in general, what would be this kind of a set is it contains a vector of this kind, which has components x1, x2, so on, xn, such that all these x1, x2, and so on, xn, they belongs to R. So this is basically a general Rn, which we call a Euclidean space. Okay. Euclidean space or Euclidean n space, you also say it. Okay. N is what? N is the dimension of that space, R power n. If you have any question, you can ask me. Now, these are very basic concepts. What kind of spaces these are, Euclidean spaces. And the elements of these spaces are basically called vectors. Okay. So now this is a vector, and it is usually denoted by x bar. On x, you have to put a bar on the vector, or under that x. Okay, and these are usually denoted by small letters, not capital letters. Okay, so this is denoted by small letter with the bar over it. So this is how we define vectors in Rn. So if we don't know what space this vector belongs to, we can count their components. How many components this vector has? N components. So this vector should belong to Rn. Now, how many vectors how many components this vector has? 4 components. So this should belongs to R4. Okay, because it's a Cartesian. It's a product of 4 real lines, 4 real numbers, set of 4 real numbers. Okay, you get it, the basic concepts. If you have any question, you can ask me.
So if it is having 5 million components, then does it mean it will be R 5 million?
Yes.
And how we are going to imagine that?
You can imagine that, but you cannot plot it. Over R3, you can only imagine what is R4. What would it look like? R4, R5. You can only imagine them. You cannot plot them. Okay. So even if it is R power 1 million, then you can imagine them in a way that there should be 1 million mutually perpendicular lines, which can make R power million. Okay.
Right, sir.
Now, these kind of spaces are basically used with the context of linear algebra. It's basically they would be used in discussing solution of linear systems. You know that if we have a linear system of 10 by 10 equations and 10 unknowns, then their solution belongs to what? Who was talking to me right earlier?
Yes, sir.
Tell me, what would be the space where the solutions lie in a linear system which has n equations and n unknowns?
Sir, n.
R power?
N.
R power 10.
Yes,
एक linear system है, हाँ, मैं सीधा आप n कह रहे हैं. So now you can imagine that we'll discuss linear system and their solutions in the context of Euclidean spaces. Their solutions, if a linear system having 10 equations and 10 unknowns, if it has infinite many solutions, then the solutions infinite many solutions. We have infinite many solutions, and the solutions are basically vectors which belongs to R10. Okay. Now let us discuss how to add and subtract these kind of vectors and how to do whether their multiplication is possible or not. How do we do the scalar multiplication of these kind of vectors? Addition of vectors. How do we add to such vectors? If we have two vectors, maybe x and y, they both belongs to Rn. When I write this thing, you should immediately imagine that x is a vector which belongs to Rn, and x should be a kind of this kind of vector, x1, x2, so on, xn. Okay, because x belongs to Rn, then x is a vector which has n components. Okay, or we call it ordered n tuple as well. Okay, we call it ordered n tuple. Okay. Similarly, we can write y as you have to define its notation, which should be different from x. So y1, y2, so on, yn. So this is a kind of vector y which belongs to Rn. Okay, it should have n components. So whenever I say this, you should immediately imagine that these are two vectors which have n components, and we can write them in this way. Okay? Now, if we want to add these two vectors, x plus y, then how do we add them? First, we write these two vectors, okay, having component x1, x2, so on, xn, and y1, y2, so on, yn. Then how do we add them? The addition of two vectors is just like the matrices. We add the respective component of each vector, x1 plus y1, x2 plus y2, and so on, xn plus yn. This is how we add two vectors. Their respective components will be added in a one vector. Okay. Now, this is how we define the addition of vectors in Rn, or you can say that addition in Euclidean space.
आपने नीचे क्या लिखा है एरो के साथ? सर नीचे बिल्कुल ordered क्या?
Ordered n tuple.
N tuple. Okay.
Tuple.
Tuple. Okay.
So when we started with the topic of matrices, we discussed what is the applicability of that topic or that thing. So when we already have one thing that can solve similar problems, what is the purpose of going directly from matrices to vectors?
Because matrices and vectors are interrelated with each other, for the first thing. The second thing, the solutions of linear systems are basically what? They are vectors. Okay. Then
Right.
if you want to manipulate the solutions of a linear system, then you should be able to discuss easily the addition of vectors, multiplication of vectors, scalar multiplication, and many other operations. In the subsequent topics, we'll discuss vector spaces and linear transformations and vector spaces and many other things, linear independence of vectors. So all these topics will help us to discuss what one thing which is the solution of linear systems. In this course of linear algebra, we will only discuss linear systems. Okay. So the first thing is how to solve them. Okay. Once you know how to solve them, then you have to go to the next step. You have a solution set of linear system. Now, what to do with this set? What kind of information we can dig out of the solution of linear systems? Now, solutions of linear systems are basically vectors. Okay. In order to discuss or in order to dig out some information from the solution set of linear systems, you should be able to discuss vectors.
Right, sir.
Who asked me this question? Moise?
Sir, Qasim.
Qasim. Okay. I hope you get it.
Yes, sir.
First,
thank you.
In this whole course, we only discuss linear systems. The first thing is how to solve them. Second thing is, once you can solve them, you get the solution set in case of infinite many solutions. If you get only one solution, then there is nothing to do with that. But when you have infinite many solutions of linear systems, then their solution must have some hidden information in that set. Okay? So we have to discuss what kind of these solutions, what information they are giving to us. So in order to discuss these kind of things, we need to discuss the form of a solution. The form of solutions are what? They are vectors. So now we are discussing vectors. Okay. Now, how to define vectors in Rn? How to add them? Okay. Now, how to do a scalar multiplication of vectors? Okay. So what is a scalar multiplication? Scalar multiplication of multiplication of a vector. Scalar multiplication means how do we multiply a vector with a scalar? Scalar is a single constant. Okay, you can say let C be any scalar. Okay, C belongs to R. Okay, C is any scalar. Okay, it's a scalar. It's a constant, and X is some vector which belongs to Rn. So you should be able to clearly see what is the difference between this and this. Okay, now what is this? C belongs to R. R is a simple real number, set of real numbers. Whenever I write C belongs to R or K belongs to R or some other constant, alpha belongs to R, then that must be a scalar. Whenever I write X bar belongs to Rn, then this X bar is a vector which has n components. It means we can write this X vector in a way x1, x2, so on, xn, because it is a vector and it belongs to Rn. Okay, because its dimension is n, so it must have n components. It's understood. You should be able to differentiate between scalars and vectors. Now, how do we multiply a scalar with a vector? So it is a scalar, we call it scalar multiplication. So x into x, c into x bar is what c times x1, x2, so on, xn. And it is usually defined, we multiply that scalar with each component. So it is c x1, c x2, so on, c xn. So this is how we define the scalar multiplication in a usual Euclidean space. Okay. In a usual Euclidean space. But we can change this definition, we'll see later on. We can define scalar multiplication or vector additions in some other way as well, when we'll discuss the vector spaces. So these are the two basic operations which we define on vectors. The first thing is how to add or subtract two vectors. The second thing is how to multiply a scalar with a vector. I hope you get it. If you have any question, you can ask me. Now, many other properties, these vectors, they have many other properties. जी बेटा.
Quiz में कितना time है?
अभी 10 minutes हैं.
अच्छा.
Okay. Now, all these vectors, there are infinite many vectors in our n Euclidean spaces. We have to discuss some other properties of these vectors as well. These are two basic operations on the vectors. Okay, how to add two vectors. Kindly mic बंद कर दें, पीछे से अजान की आवाज आ रही है. Who is this guy whose mic is on? Thank you. Hello. Again. Not again. I have to mute all.
Switch off your mic.
Who is this guy? Okay, Ahmed Jamal. आपको भी म्यूट कर रहा हूं मैं. So that's good now. Now, other properties, these are two basic operations. These are not properties. Okay, basic operations defined on Euclidean space. Now, the properties is that the first property is that you can say that any two vectors x, if we have x plus y, then it is equal to y plus x. Means they are commutative. If we say that if x, y, they belongs to Rn, then x plus y is equal to y plus x. What we call it commutative property. Commutative law or some property, you can say that. Okay, commutative property with respect to addition. Okay, with respect to addition, vector addition. Okay, with respect to, you can say, vector addition. Okay. And how do we define vector addition? This is how previously we defined vector addition, how to add two vectors. So you have to specify here when this property is true, it is a commutative property of vector addition. Okay, so you should know how to add two vectors. Previously, we defined these operations. So this is the first property which these kind of vectors in Euclidean spaces, they satisfy. Other properties which we can discuss are kind of, let me discuss them very briefly, and we'll discuss them in detail in the next lecture. Other second property, you can say that x plus y plus z. Okay, these are three vectors, and this is equal to x plus y plus z. These are again three vectors. Now, you cannot add three vectors directly. तीन नंबर्स को डायरेक्टली तो ऐड नहीं कर सकते ना. पहले दो नंबर्स को ऐड करेंगे, जो उसका आंसर आएगा उसको तीसरे नंबर में ऐड करेंगे. Similarly, this happens in vectors as well. You can add any two numbers first. X plus y को पहले ऐड कर दें, बाद में z ऐड करें, या आप y और z को पहले ऐड करें, बाद में x ऐड कर दें. It doesn't change anything because you cannot add three numbers at the same time. You have to add two numbers first, and then you have to add the third number in the resultant of that sum of two vectors. So this is called associative properties where X, Y, Z, they are, in fact, they belongs to Rn. And this is called associative property. Okay. Associative property of vectors, of vector with respect to, you can say, with respect to vector addition, usual vector addition. Okay. How to add these two vectors? How do we add these vectors as we defined earlier? Okay. Why I am specifying here or stressing over here vector addition? Because all these properties, they also exist for some other spaces with respect to multiplication as well. Okay. In that case, we say that the associative law or commutative property, it can be true for some other kind of elements. U into V is equal to V into U. Okay. Similarly, U into V into W, it could be is equal to U into V into W. So these kind of properties are basically commutative property and associative property with respect to multiplication. But the multiplication is not defined here. Okay. We'll discuss these kind of properties later on. We'll discuss when we'll discuss vector spaces. So I'm stressing over here that this associative property is basically true for vectors with respect to vector addition. Okay. The third property which we usually have in this vector things is, let me define it in a proper order so that later on you don't have any issue. Yes, additive identity. Next is additive identity. Now, what is additive identity in real numbers? If we define R as a set, okay, as a set minus infinity to plus infinity, then if we take any number in R, for example, 2, so what is additive identity? A number which we add in this 2, which we add in this number 2, and the result of that addition gives us the same number, 2 again. That will be the additive identity of this number. So what we can put here to get the 2 again in real numbers? Anyone?
0.
0. So 0 is what? 0 is additive identity in this real numbers space. Okay, this is a set now. Space now, we call it space. So 0 is the additive identity in R, because whenever we add 0 in any element, in any non-zero element of R, it gives us the same number. Okay. Now, what would be, and usually we denote identity by the letter E, and E is 0, which belongs to R. Okay. What is the additive identity in vectors in Rn? So we define it 0 vector, and it has all the entries 0. So this is what? This is additive identity in Rn, because this vector, when we add it to any other vector, that vector won't change. So this is we call additive identity, and we usually denote it by E bar. Okay. In spaces. We'll discuss, we'll start discussing in the next lecture with the additive identity again. I'll explain it a little more to you, these things. Now, the quiz is, I think, open on LMS. You can start doing quiz.
Sir, is it due at 1:45 or 1:55?
1:55, including uploading time. Okay.
And it's not a copy paste, ठीक है?